I'm Ludo, and on this channel we take a data-driven approach to sports car performance. Today we are kicking things off with an aerodynamic test on my Porsche 718 Cayman GT4 using a simple but powerful technique, TUF testing.
TUF testing is a simple yet effective way to visualize how air flows over a car's surfaces in real time. By attaching small strands of yarn to key areas, we can observe whether the airflow stays attached, separates, or becomes turbulent at speed. This method is commonly used in motorsports, prototyping, and DIY projects because it provides instant visual feedback that helps identify areas of aerodynamic inefficiency. For our test today, we'll be looking at key areas like the hood, rear window, wing, rear diffuser, and rocker panels to better understand how air interacts with the car. The car is unmodified, so this test aims to establish a baseline for future comparisons while identifying potential areas for improving downforce and reducing drag. The materials needed for this test are inexpensive and easy to find. We'll be using wool yarn in different colors, ideally contrasting with the surfaces that we'll apply it to. For my GT4, I'll use white yarn for the painted surfaces and red yarn for the glazed ones to ensure clear visibility. To quickly create a large number of tufts, a simple method is to wrap the yarn around your hand or fingers, depending on the desired length. Then, cut along one side with scissors. For attachment, I'll be using painter's masking tape. It allows for easy application while ensuring the painted surfaces remain undamaged. If the car is waxed, it might be difficult for the tape to stick to the surfaces. Wiping the surface with isopropyl alcohol removes the oils and allows the tape to stick. I positioned a drone at the side of the road to film the car driving by, then made several passes at approximately 35 to 40 miles per hour. For TUF testing, increasing speed beyond this range does not yield additional insights. Since I couldn't pan the shot as the car passed, I manually adjusted the drone's position to capture different angles. To minimize motion blur, I also set the shutter speed as high as possible. For close-up shots of key areas, such as the wing, diffuser, sides, and hood, I use a GoPro mounted in strategic locations. Careful consideration was given to the camera's mounting position and orientation, as any attachment on the car's body could disrupt airflow. To minimize interference, I positioned the camera to capture airflow either upstream of its location or far enough away that its presence wouldn't affect the flow dynamics. Reviewing the footage, the drone shots didn't turn out as well as I had hoped. You can see the car is in the frame for only a brief moment, making it difficult to interpret the raw footage. To improve usability, I significantly slowed down the footage without using any frame interpolation, preserving the original picture quality. This resulted in a video with a choppy frame-by-frame appearance, but made the footage easier to analyze without introducing any artifacts. Let's take a look. From the frontal shots, we can see that airflow appears well attached across the entire front end, except for what seems to be a small separation bubble at the very bottom of the windshield. On the sides, separation is clearly visible behind the front wheel, despite the presence of air curtains. It's also worth noting that during filming, light wind conditions may have negatively influenced the airflow patterns. The airflow appears to reattach roughly 1/3 of the way down the door, then flows smoothly into the engine air intake. However, the intake scoop seemed to introduce some turbulence just before the rear wheel. Beyond the rear wheel, the flow clearly separates again, generating turbulence before entering the wake. In all the shots, airflow over the greenhouse and most of the upper half of the car remains well attached, despite the turbulence introduced by the rear view mirror. Now, let's take a look at the close-up shots from the GoPro. This first close-up shot provides a view from the roof, looking over the hood and windshield. In this footage, the separation bubble at the base of the windshield is clearly visible, indicated by a couple of laughing tufts. Additional details that weren't visible in the drone shots include the light turbulence caused by the small gurney flap on the front radiator vent, just ahead of the hood, and what appears to be slight separation at the inner edges of the front fender wings. The second close-up provides a detailed view of the airflow over the rear window and wing. In both areas, the flow remains attached and appears very smooth, with only the far right tuft on the wing flattening slightly, possibly caught in the vortex generated by the wing end plate. The next shot is particularly interesting, providing a detailed view of the airflow beneath the wing, over the rear window and across the spoiler. The flow over the rear deck lid appears smooth and well attached, as does the flow beneath the rear wing. This indicates that the wing airfoil is functioning as intended, generating downforce. If the tufts under the wing displayed separated flow, it would suggest the wing is stalled, either due to an excessively steep angle of attack or because it is operating in turbulent airflow. In such a scenario, the wing will behave more like a spoiler rather than an effective airfoil. Another intriguing detail is the increased turbulence over the ducktail spoiler, where the tufts are flattening upward. I initially expected to see attached flow on the spoiler, followed by turbulence further downstream, but that's not the case. My interpretation is that this behavior results from the interaction between the spoiler and the wing, with the wing generating a low-pressure zone beneath it that is lifting the tufts on the spoiler. Or maybe my interpretation is completely off and this is simply the typical airflow behavior over a ducktail spoiler. Let me know what you think in the comments below. The rear diffuser shot is also very interesting. On the GT4, only the central section of the diffuser appears to be aerodynamically active, with Porsche claiming it contributes to approximately 50% of the rear axle's total downforce. In this footage, it's easy to see that the tufts in this section remain in attached flow, being pulled tightly against the diffuser's surface. This confirms that the diffuser is functioning as expected, generating low pressure in the rear section of the undertray. However, at the sides, it is evident that the tufts positioned outside the central section are fluttering in the car's wake, indicating flow separation in those areas. This side view once again shows well-attached airflow across the entire upper section of the bodywork. Also visible are the tufts fluttering in the detached flow behind the front wheel. The turbulent wake generated by the rearview mirror appears to have minimal impact on the airflow over the side window and the upper portion of the door. This is further confirmed by an interior view of the side window, which shows attached flow on both the side window and the windshield. In this view, taken from above the rear wheel arch, we again see mostly attached airflow along the side. The flow separates behind the front wheel, reattaches about 1/3 to halfway down the door, and then becomes slightly turbulent after passing the engine air intake scoop. While the airflow remains attached around the A-pillar and side window, the tufts being pulled upward near the A-pillar suggest the possible formation of a vortex in this area. These additional close-up side views show how the tufts on the lower side of the body and the rocker panel are being drawn downward toward the ground. This could be caused by a low-pressure area generated by the diffuser, pulling air from the sides beneath the car. If that is the case, it might be possible to enhance downforce by improving the sealing between the sides and the floor, preventing air from rushing in from the sides. After filming the videos, I took a series of still photos with the car stationary. This turned out to be quite interesting, as the tufts clearly reveal areas where the airflow was strongly separated. It's easy to notice that the tufts in these regions appear split and frayed. while those that remain in attached flow show little to no wear. So, these were my initial impressions after reviewing the footage. What do you think? Let me know in the comments. In the next episodes, I'll continue this analysis by measuring aerodynamic pressures to better understand how lift and downforce are generated. If you enjoyed this content, be sure to subscribe, hit the like button, and stay tuned for more in-depth testing and performance-focused modifications.